Hello, everybody, and welcome to our last lesson of our chapter 7-8 chapter. We're going to be looking at graphs of exponential and logarithmic functions today. And so we're going to start with a very basic exponential graph and use that to come up with some rules for all exponentials. Pretty much past that, if you can identify the base graph, then you can use transformations from chapter 1, which we've been using all along. We used it in our conic section. We used it in our chapter 5 with trig functions. So once you have the base graph and you know what that looks like, you can use transformations to move this around and graph much more complex problems. Also, generally, these types of questions, you would probably use something like Desmos to graph. So understanding what an increasing versus decreasing function looks like, and what does a typical exponential versus logarithmic function look like, where do the asymptotes go, and things like that, are really what we're looking for in this section, especially with our distance learning right now. So we've been asked to graph y equals 2 to the power of x here, and we're going to use a table of values to start. Once you know what the basic ones look like, you probably won't need a table for every one, but again, a table can be useful if you have a bit harder time with graphing. So I'm going to make myself a table of values. And I'm going to just pick some basic values, -3 to 3. So I'm going to go -3, -2, -1, 0, 1, 2, and 3. Now remember, y is just 2 to the power of x. Okay. So for this first one, if x is -3, we have 2 to the power of -3, which remember is 1 over 2 to the power of 3 from our negative exponent rules from way back in grade 9 and 10. And 2 to the power of 3 is 8, so this would be 1 over 8. So this is a really gross number to try and graph. If I go on my graph over to -3, like we can't even really draw this by hand. This would be very difficult. Okay. If x is -2, we have 2 to the -2, which would be 1 over 4. So again, if we're on our graph, trying to graph this, it's not going to look a heck of a lot different than the 1 over 8 y value, because we're not computers, we're humans, and trying to graph this particularly on such a small little square is hard. 2 to the power of -1 would be 1 over 2. This one's a little easier. It goes up a little farther here. If I had x is 0, this is 2 to the power of 0. We know anything to the power of 0 is 1. Then we've got 2 to the power of 1, which is 2. Then we've got 2 squared, which is 4. And then 2 cubed, which is 8. So once you have a positive exponent or a positive x value, those points are obviously a lot nicer to draw. The negative exponents, or the negative x values, we end up with these fractional values for y, which kind of suck, right? They're not very nice. They're hard to draw by hand. Maybe we can connect our dots. We're going to put arrows on the end because if we had chosen different x values, these would go forever. Now you'll notice that no matter what x values I choose, if I kept going on my graph over to the right with bigger and bigger x values, this graph would go up forever and ever. Okay, this would keep going up that way always. Okay. The smaller and smaller x values I choose as I go to the left, so -5, -6, -7, these fractions are going to get smaller and smaller, but they will never actually touch the x-axis. There is no exponent we can put on this base of 2 to the power of something. There's nothing we can put there so that this equals 0. So this will keep going to the left forever and ever, getting really, really, really close to the x-axis, but technically it will never touch. So we actually have an asymptote here. We don't usually draw it in. Usually we just leave it, but it's there. Okay? So this will be true for every basic exponential function. Our asymptote is at y equals 0. So unless there has been some sort of vertical translation moving this up or down, every basic exponential function will have a horizontal asymptote at y equals 0. So when I say that, I mean like if I had something like y equals 2 to the power of x plus 1, that would be moving up 1. And so my asymptote would move up 1 as well. Okay. Or if it had a minus 5 at the end, we'd be moving down 5. Okay. The next piece of information is an intercept. Okay. We don't have an x-intercept because the x-axis is an asymptote. And we can see from our graph our y-intercept is 1. Or if you wanted to do the coordinate of the point, it would be 0, 1. Again, unless you have moved this graph up or down, or if you had a vertical expansion or compression, this will always be your y-intercept of a basic exponential function. So if my exponential function was y equals 5 to the x, my intercept will be 1. Y equals 4 to the x, my intercept will be 1. If all of a sudden I said 5 to the x plus 1, now my intercept would move because I would move that graph up 1. Okay, so a basic exponential function, something to the power of x, will have a y-intercept of 1 and no x-intercepts. Our domain and range, we know that we can plug in any x value we want. There's no restrictions there, which means my domain is all real numbers. My range, we see that all of our y values are positive or above the x-axis here, but we can't actually touch the x-axis, which means our range is greater than 0, but not equal to 0, because when y is 0, we have a horizontal asymptote. So just some notes about graphing exponential functions. Every basic exponential function y equals a to the x. Okay, so if it's just a basic one like this, we'll have no x-intercept, a y-intercept at 1, an asymptote at y equals 0, a domain of all real numbers, and a range of y is greater than 0. Okay. If you have some other exponential function, transformation rules apply. Okay, so transformations apply. So if I have y equals negative 2 to the power of x, this would be a vertical reflection. Okay, what that means is that my graph would no longer look like what it looks like up top there. It would now look like this, which means my range would change, my y-intercept would change, my asymptote would not change. If we have y equals 2 to the power of x plus 2, this means that our entire graph would move up by 2, including our asymptote. Okay, so all of our transformation rules apply to these functions. The other type you might see is if you have some y equals 1 over a to the x, meaning the base of your exponent is a fraction, this is still going to look like the true graph, but decreasing. So the one we have increases as you read the graph left to right, goes up. If you have a fractional base, this one will decrease as you read left to right. Okay, but it still looks like the graph above in the sense that we have the same domain, the same range, same y-intercept, same x-intercept and the same asymptote. Only difference is that it almost looks like a reflection horizontally, and basically it's decreasing as you read left to right, it's going down instead of up. Okay. So on the next page, I am asking you to draw y equals 3 to the power of x. And we're going to again use a table of values to help us. So if you'd like to pause the video here and try this yourself, you can. If you feel like you would like to be walked through one more, you keep watching. So we are trying to graph y equals 3 to the x. So again, I'm going to go -3, -2, -1, 0, 1, 2, 3. So 3 to the -3 would be 1 over 27. I'm not even going to try and put that on my graph. 3 to the -2 would be 1 over 9. That's going to be real hard. Okay. 3 to the -1 is 1 over 3. 3 to the 0 is 1. 3 to the 1 is 3. 3 squared is 9. That one actually goes off our grid already. 3 cubed is 27. That's not going to fit on our graph. So again, we can see here that we have a y-intercept of 1. We can pick any x values we want. As we go to the left, we're going to get closer and closer to the x-axis, but never touch. As we go to the right, we're going to go up forever. So we have x-intercept. We've got our domain is all real numbers. We've got our range is bigger than 0. All the same as before. Now, part B is asking us to draw the inverse on the same grid. So just a reminder, for an inverse, the coordinates of the points switch. So what I mean by that is on original graph, we have a point 1, 3. Then on inverse, the point will be 3, 1. The points are literally going to swap. So I'm going to work my way left to right. So my first point that I drew here had an x value of -2 and a y value of 1 over 9. This means that now my x value will be 1 over 9 and my y value -2. The next point I drew was an x value of -1, a y value of 1 over 3. If I switch these, this is now an x value of 1 over 3 and a y value of -1. Next, I had x is 0, y is 1. This means now I'm going to have y is 0, x is 1. Then I had 1, 3. This will now be 3, 1. And then I had 2, 9. This will now be 9, 2. So this is the point that was a little bit off of our graph before. So if you recall from way back in chapter 1, an inverse was a reflection across the line y equals x. So you can see this looks like a mirror image. If we wanted to find the equation of the inverse, we needed to swap x and y, then resolve for y. So our original equation was y equals 3 to the power of x. We want to find the equation of the inverse. We would swap x and y, which would give us x equals 3 to the power of y. And then we need to solve for y. Now, because we want to find y, that's our unknown, which means we have unknown exponent. This means we need to log both sides so that we can find that unknown exponent. So if I log the left and log the right, using our log laws, we can bring that y down. Now, if I divide both sides by 3, I get log x over log 3 equals y. Now, this is not normally how we would write this. We would use the change of base rule that most of you would not be using because you've got the fancy calculator. But those of you who don't have the fancy calculator will be more comfortable with change of base. Change of base said that we had log base 3 of x equals y. And we know this to be true. We know that if x equals 3 to the power of y, if we want to rewrite this in logarithmic form, the base of that exponential up here is 3. We know that the inside stuff is what this equals, which is the x, and then the exponent is what the log equals. So we know from back in lesson 1, changing from exponential function to a logarithmic function, we know this is true. We could have gone straight here. We know that if we have a to the power b equals c, this is the same as log base a of c. And we've already discovered that exponentials and logarithms are inverses of each other. So for our inverse graph, okay, our x values in our table of values for the inverse function. So if I made a table of values for my inverse function, oops. Okay, we know our x and our y values swapped. So our y values that we used were 1 over 9, 1 over 3, 1, 3, and 9. And our x values from our original table are now our y values, which were these. So our table is literally just a swapped version of our original table, but I'm not using the 3 and the negative 3. They didn't fit on our picture very well. So our x values are all powers of 3. So if we didn't have 3 to the x, they would be powers of whatever your base was. Okay. So it says this should give you a hint as to how to create a table of values for any logarithmic function. So we would want to use the powers of the base as our x values. Okay. So for example, let's say I wanted to do log base 5 of x equals y. If I wanted to make a table of values, I would want to use powers of 5 as my x. So I might choose 1 over 25, 1 over 5, and then 1, and then 5, and then 25. And then my y values would be -2, -1, 0, 1, and 2. So these are all essentially, if I want to think about this as an exponent, this is 5 to the y equals x. So these are all the exponents here. And then these are all of the powers of 5 here. So when I make a table of values for logarithms, I always change it to 5 to the power of x and basically pick y values and pop out x values. It's not really the way you're supposed to do it. You're supposed to pick powers of the base and then figure out what exponent that would be. So pick the x values and figure out what y values go, but I don't like to do that. I find it too confusing. So I always choose to rewrite it and do it that way. Okay, so we're going to try another question. So if I wanted to graph y equals log base 4 of x, I'm going to make myself a table here. So here's what I would choose to do. What the book wants you to do and what the course wants you to do is say, okay, what are some powers of 4? And write those in the x column. and then figure out what exponents go with that. I would choose to rewrite this as to the power of y equals x. And then I'm going to pick some exponents or pick some y values. So a good exponent might be -2, -1, 0, 1, 2. I'm basically going to build my table backwards. Instead of picking x values and popping out y's using the log equation, I'm going to pick y values and pop out x values using the exponential version. So if my y is -2, my x is 1 over 16. And then if y is -1, I get 1 over 4. Y is 0, I get 1. Y is 1, I get 4. And if y is 2, I get 16. So I build my table backwards for log functions. I find it makes more sense. You do not have to do it that way. You can pick powers of x and then figure out y after. So 1 over 16, I'm not going to try and graph that. 1 over 4, -1, I can graph that. X is 1 and 0. X is 4, y is 1. And again, x is 16, y is 2. Like that's way, way, way off your grid. So I'm not even going to try and graph that one. And I know for my logarithmic function, my asymptote is now here. My asymptote is x equals 0. So notice that your exponential, your asymptote was y is 0. For your log, your asymptote is x 0. We have no y-intercept, and my x-intercept is at 1, or 1 comma 0. My domain is x is greater than 0, and my range is y can be all real numbers. Notice this is backwards from your exponentials. Your exponential function had no x-intercept and our y-intercept was 1. Because this is an inverse, these swap. We now have no y-intercept, x-intercept is 1. Okay? As with exponentials, this will be true for all basic log graphs. So if there's no transformations, so it's going to be of the form y equals log base a of x, where a is some integer, okay? So log base 5 of x, log base 6 of x, log base 7 of x, any base there I put in, I will have asymptote at 0, x equals 0, a vertical asymptote. I will have no y-intercept, and I will have an x-intercept at 1. My domain will be x is greater than 0. My range will be all real numbers. Okay, we're going to try one more question here with some transformations. So the log graphs with transformations give people the most difficulty. So we're going to identify the transformations here. So we've got a 2 in front. Remember, a number in front of a function would be a vertical expansion by 2. We've got a +3 at the end. This is going to give us an up 3. Now we have a problem here. We have a 2 inside brackets with the x. Remember, we always need to factor that horizontal expansion compression out. So we're going to rewrite this as y equals 2 log base 4. We're going to factor this 2 out, and then our brackets will end up being x plus 3. Now, we can see that we've got a +3 in the brackets. This would be left 3. Okay. And we have a 2 in front of the brackets. This would be a horizontal expansion by 1/2. So recall from chapter 1, your horizontal expansions and compressions are always backwards to both things. It says 2, so that means it's actually by 1/2. Okay. So we're going to need to graph this thing. So I would choose to graph my base function first, which would be log base 4 of x. Then I would do my horizontal expansions, compressions, vertical expansions, compressions, and any reflections. Then I would move up, right, left, down. Okay. So my very base function is the one we just drew above, which looked like this. We had another hidden one over here. This point here was 16.2, way off the grid. Okay, so this is y equals log base 4 of x. That was the very original basic graph, no transformations. So as with chapter 1, I'm going to choose to draw what I call a ghost graph, which is after my expansions, compressions, reflections. So if I do that, I'm going to do that in red. Actually, no, I'm going to want red for my asymptotes. So maybe I'll do. So if I do a vertical expansion by 2 and a horizontal expansion by 1/2, if I start with my leftmost point, this point here was originally a y value of -1. Now it's going to be -2. And originally it had an x value of 1/4. I take that in half, that's now 1/8. It's super close to the axis. My next point has a y value of 0. So if I times that by 2, it doesn't move. But a horizontal expansion by 1/2 will cut that down to a half. The next point has a y value of 1. If I expand that by 2, it goes up here to 2, but not actually, because we also have to do our horizontal expansion by 1/2. So my y value will now be 2, but my x value will now be 2 as well. Now, these were all the points we fit on our original graph we drew up above, but we do have that point that was way off the grid, which was 16.2. So if I take my horizontal value and cut that in half, that would now be at 8. And if I double my y value, I'd now be at 4, which I can include on my graph here. This would now be at 8.4. So I can draw this in. Now, notice how my asymptote would stay on the axis for now because we're only dealing with expansions and compressions. My asymptote's at 0, so any expansions, compressions will not move that asymptote. However, my asymptote will move when I move this thing left, right. So once I move this thing right, I'm going left by 3, up by 3. So all these points in green need to move left 3, up 3. So I'm going to start with the leftmost point. If I move it left 3, it's going to be almost on x equals -3, but not quite. And then up 3, it will end up here. The next point, left 3, and up 3, will end up about here. And then the next one, left 3, up 3. And then the next one, left 3, up. So my asymptote originally was on the x-axis here, my very original asymptote. Expansions, compressions would not move that, but moving left 3 would. So now my asymptote is here at x equals -3. Okay, so the blue one is my final graph. The green is after only my expansion compression. Okay. So my asymptote is now at x equals -3. And that's because we moved left 3. My intercepts, we could look at our graph, but they would be kind of hard to find. They're not in nice places. So we can actually find these algebraically, but it is messy. So if you were to graph this on Desmos, you'd be able to find a nice decimal value for each of these, but we can do it algebraically as well. So graphically, you'd probably want to use Desmos. You wanted to do this algebraically, which I'll do on the bottom here for you in case that's what you would want to do. For your x-intercept, remember this means that y is 0. And for your y-intercept, remember this means that x is 0. And we can see we're going to have both. From the graph, we cross both sets of axes here. Okay. Your domain would be x must be bigger than -3, but not equal because it's an asymptote. And your range would be all real numbers. So if I wanted to actually find my intercepts here, I'll show you how to do that algebraically. Your y-intercept, x is 0. So you'd have y equals 2 log base 4, 0 plus 6 plus 3, or 2 log base 4, 6 plus 3. You can plug that into your calculator, and you would get about 5.85. Again, if you don't have one of the fancy calculators, for a log base 4 of 6, you might need to use change of base. For your x-intercept, your y is 0. So you'd have 0 equals 2 log base 4, 2x 6 plus 3. You need to find x here. You need to try and isolate x. So I would move the 3 over to the left. Divide both sides by 2. And then I'd rewrite this in exponential form. So you'd get 4 to the power of -3 over 2 equals 2x plus 6. And then you can move the 6 over. Then you can divide by 2, and I would plug that into my calculator as well. So I would divide by 2 here, divide by 2. And then on my calculator, I get x is approximately -2.9, which if I look at my graph makes sense. So again, our big thing we want you to know here is we want you to know what a logarithmic graph looks like, and that the basic ones have an asymptote on the x-axis, on the y-axis, with no y-intercept, and an x-intercept of 1. We want you to know that an exponential function has an asymptote on the x-axis with no x-intercept and a y-intercept of 1, and what these things look like. So what a basic logarithmic graph looks like. What does a basic exponential graph look like? What are your domain and range for those things? Okay. So as you go through trying practice questions, of course, you can always plug these into Desmos to see if your answer makes sense and if it works. Okay. But we're looking for, do you understand what these things should look like and where the asymptotes, domain and range, and intercepts would be?